Welcome back, guys. So in this video, I'm going to start by showing you the work for the problem we ended class on Friday with. So this is the exact same paper from class. We were doing the limit as x approaches 0 from the right of x times ln of x. And in class, we had gotten to about here, where we wrote it as ln of x over 1 over x, aka x to the -1. And then I said, the answer is 0, class is over. So if you would like to see the rest of this work here, it's what I have kind of underneath that last step from class. So I applied L'Hopital's rule in this step, took derivatives. This was pretty gross, so I took a minute and just simplified what I had so it was something easier to look at. And then realized that it was a function I could just plug 0 into, and I got 0. So if you want to take a look at that, feel free to pause this video on this page, and then otherwise we'll move on. So in class, we said there are two special cases of L'Hopital's rule. This was one of them where you have to kind of rearrange at the beginning. And then this video, the rest of this video will be about the other special case. So the other special case is for limits of the form. Find my paper here. It's 0 raised to the 0 power. That's a mystery indeterminate form. 1 raised to the infinity power. Same deal. It's not super obvious what that limit would go to. Or infinity raised to the 0 power. Okay, so the crux of what we're about to do, like we're going to use L'Hopital's rule for sure. But there's going to be like one really significant move that we do in rearranging the limit that we start with. And the crux of it is this. If you have any function in your limit, it is equal to e to the ln of that same function. Now, it looks like we've made it much, much worse. So e raised to the ln of something, they cancel each other out. And this really is just equal to the f of x in the ln here. The reason that we would want to write something this particular way is because of log rules. So f of x will have some exponential form to it, right? These are all exponentials. So it'll have some exponent that can come down out front using the exponent rule. So we're doing this because using that log rule is so useful. So let me show you what I mean. The example we'll do first is limit as x approaches 0 from the right of x raised to the x power. So if we think about what this limit form is, we say, okay, well, the base is definitely going to 0. The exponent is definitely going to 0. So this fits that first type here. So this is an indeterminate form, meaning things that have this format, they end up with all different answers for the limit. Like it's not obvious what it will end with, like it's a mystery still. 0 to any power feels like it would be 0, but then any number to the 0 power should be 1, right? There's like competing forces. So we're going to use exactly this trick here. So instead of x to the x, I'll write it as e to the ln of x to the x, which looks worse, but will be helpful. My pen is dying, so I'm going to switch into green for the rest of this. Okay. So now I am going to bring this exponent down out front. We're doing this all with exponential forms, so that'll always happen. Okay. So we have e raised to the x times the ln of just this one base x is left over. So this exponent rule, if you're not familiar with it, what you're seeing is exactly what you'll need from it, which is any exponent on the like interior of a logarithm can come out front as a multiple, and they're equal to each other. Now, because e to the x is a continuous function, the limit can really just be up here, right? So it's e raised to whatever this is headed towards. So this limit notation, I'm going to put all the way up top so I can kind of zoom in on the problem area. Nope, I've already screwed up. It shouldn't start with limit anymore. It should start with the e. So I have e raised to the limit as x approaches 0 from the right of this x ln of x up top. So for the rest of the problem, I just need to compute what this is. Whatever I get for a number there, I'll say, okay, e to that is my answer. The reason that this is in the L'Hopital section is because the way that these start, what you get here is a L'Hopital problem using the last trick. Okay, so what I just did was weird, but it's the same steps every time. So let's recap before we continue. It's 0 over 0 form. So I said, okay, it's one of these three. So what I'll do is write my function as e to the ln of my function. Then take the exponential part down out front as a multiple. And then bring the limit up into the exponent. So it's e to the limit of whatever's happening up here. Then we can zoom in, compute that limit, and then e to that number is our final answer. And I'm going to be extra cute here. This is the example we just did. So we're going to reuse our work a little bit. So this was x ln of x. Flip back here. We already did this. So if we hadn't already done it, in a regular problem, we have all this work that we do, and we get to a final answer, which is 0. So we're going to take that 0, come back over here, and say, okay, this limit is equal to 0 because I did L'Hopital's rule. So my final answer is e to that 0, and e to the 0 power is 1. So this limit is equal to the number 1. That was fun, right? Okay, let's do one more problem. I'm going to just talk right through it, but if you want to try it on your own, which I highly recommend, as soon as I write down the limit right now, pause this video and try it, and then start playing me to check your answer. So the next one we'll do is the limit as x approaches 0 from the right. And we'll have 1 plus x raised to the 1 over x power. This is a weird limit. So we always want to pause or at the beginning here and just double check what form this limit is. If it's not an indeterminate form, we may just get a number. So if x is approaching 0, 1 plus 0, the stuff in parentheses, that just approaches 1. But then the exponent, 1 over x, approaches infinity. So we're going to say positive infinity just because x is approaching 0 from the right. So 1 over teeny tiny positive number is headed toward a very large positive number. And this fits the second type in this list. So we know that the method that we did above will work. It's just going to take a lot of scratch work. Right, so I'm going to copy the steps here, e to the ln of this function, bring the exponent down, bring the limit up, then zoom in just on that limit. E to the ln of the original function, which looks very hideous, but it'll start to get a little bit better. This 1 over x exponent up here, because it's inside the logarithm, can come down out front and be a 1 over x out front. So just 1 plus x is left over in the ln. And then my last move, like I did here, was to bring this limit up into the exponent part. Because whatever this is, it's going to be e to whatever this is doing. Space, so we'll do e to the limit of 1 over x ln 1 plus x. Okay. So this has just kind of morphed into a different problem. This is the limit that I want to do on the side. It'll call for L'Hopital's rule. We'll get a number, and then my final answer to this problem will be e to the whatever that number is. All right, so we'll come back here with our number once we're done. But on the side now we need the limit as x approaches 0 from the right, 1 over x ln of 1 plus x. Now, just like the example above, this isn't immediately in the format for L'Hopital's rule. As it is, this is an infinity times 0 limit. 1 over x goes to infinity with tiny denominators, and ln of 1 is equal to 0. So this is like that first special type of L'Hopital situation where we're going to rewrite it as a ratio, then do L'Hopital's rule. Because it's times 1 over x, the easiest thing to do is to just have ln over a plain x. So I'm just going to reformat it. I haven't actually taken anybody's derivative yet. I'm just putting this 1 over x on the bottom as a regular x. Now we have a 0 over 0 limit, so L'Hopital's rule applies. I'll say, okay, I can take derivatives of the top and the bottom separately. I'll use my fancy L to indicate that's what I'm doing in this step. The derivative of ln of 1 plus x is 1 over 1 plus x. Technically the chain rule, but then there's a times 1, so I'll just leave it as is. And then the derivative of x is just 1. That divided by 1 down there doesn't need to be there, so I'm going to get rid of it. So this is a little bit easier on the eyes to compute. 1 over 1 plus x is something I can just plug x equals 0 right into, and I get the number 1. Right, 1 over 1 plus 0 is 1. So this is the number that's going to come back up here. We said, okay, this limit is equal to 1. So the limit I started with is going to be e to that power. And then e to the 1 power is just e. So my final answer is that this limit is equal to e, which is actually really nifty, right? It doesn't look like e would have come out of here. Fun fact, this limit is actually one of the ways that people define the number e. How it can actually be defined. Okay, so let's just end on a recap here. What just happened? We started with a limit that we recognized was one of those indeterminate forms listed above. So we know that the trick that we pulled in that first example up top will also work here. So we did exactly the same steps. We wrote our original function as e to the ln of that function. Then the exponent part of it came down out front using an exponent rule. And then we brought the limit just up to the exponent part, which is safe to do. So then we had scratch work on the side to compute this limit, which called for L'Hopital's rule. It will every time. We did a whole bunch of work and got that it was 1. Oops. So then we came back up here and said, okay, e to that number is my answer. And this happened to simplify to just the number e. Right, so those steps will be common to all the examples of this type. There's at least one of them in your web work homework, and it'll follow this example really closely.